So this is the company that monitored the bridge movement. The transporter, it turns out, that's another company, the Florida, and they also the National Highway Department, all state that you should be using a separate company to monitor your bridge movement, and also that they basically participate in the drawings at some point to determine where structural reinforcement should go, so they can add their mobile units to it and take the loads of whatever the structure may be. This company is BDI that clearly states that they are responsible for the engineering, moving the bridge. They posted this before the bridge collapsed. They were pretty proud of it. I'm not saying they did anything wrong. I'm just sharing that data. So this is hopefully maybe one of the last videos I do on this. It helps explain what's going on. A lot of people ask me in private questions about these details, and so now I'm giving these details. With that said, I do make some mistakes in my videos. I'm doing these things live. You know, they're pretty long, as you see, and you have one thought in your mind, and sometimes you do get the thought twisted and backwards. And then, of course, when this troll catches me getting something backwards, instead of saying, "Hey, did you mean that?" Nope, they'll troll me, pound me into the ground for saying 2 instead of 3 or something similar. All right, so I do not think the bridge was put in backwards. I think that that's what my favorite troll has been. It's the node that, per the drawings, did not have specifications showing that the number 10, 1011 node had any post-tensioning at all. But of course, these plans could have been amended. So we're just working with the plans, and even if they weren't amended now, or the post-tensioning was allowed in there, it's still an issue. And as you might see, the gamma at the end of this video, you'll see that how they should have used different testing before they just determined that things were no good. It's a gamma tool. It's like an X-ray tool. Awesome tools. Okay, here's roughly a layout. The top canopy, that can be a lower deck if you like. And this is the area in question. This is number 1011. Of course, that's 12. But let's just pretend like this guy right here is number 12. And this is the top canopy with nothing else attached. Closest to the last point of where the transporter was for this machine, for the bridge, was around number 10. So you can. This is pushing up. The gravity of this is pushing down, and the weight of it also is pushing down. So those are the forces. So the load from here back, from this number 10 back, is pretty much being directed back to here. Then we have the lower deck weight. We have number 12 weight. I'm sorry, number 11 weight, number 12, and the canopy weight. All now just, if you can consider that flying away, the overhang, this whole section here. Now let's go ahead and just show this. I'm just holding this, and this has nothing on the bottom yet, and no cross members. I'll glue some on in a second, so bear with me. As I push down on top of this guy, I had to put a crease there to make this more visually effective, if you will, because it wasn't moving that easily. Okay, so here we go. So now we have the this member here, number 11, put in. Now you can see that this acts as one piece now. This is tied in, if you will. The post-tensioning, also the node, the concrete, etc., is tying it in, but the post-tensioning is also, you know, not also, but is. So now it becomes a piece without flex, if you will. Still has dead weight, so that dead weight will want to flex, except for you can see that it's not flexing in this small scale, of course, but hold on for a second. So it's not flexing in this small scale. It's not going down towards the table if you look at the table reference. Now we're going to put a little weight on it, and we're going to show you what happens here. I'm going to start adding pieces back, and they're going to be glued pieces, making it a a joint, acting like a joint, not just like a single piece of cardboard I could have cut out. I wanted it to be glued. So now what I did was I took the end off my tri-square, if you will, and I'm holding here because I can't hold it behind it, but I'm holding it at the joint. But you see that it's not, it's got a lot of tension in here now, and tension in here, and at the joint also, where it's all the weight is being transferred. So now we have what you may see is a triangle, a clear triangle, and then we have another triangle offset up here, roughly, in real life also, roughly. The triangles, just you push on one, they just keep circulating their load, if you will. It's not quite as simple as that, but imagine that. Now I still have the gravity weight I put here to try to show that no deformation is taking place. It would be very difficult for me to create flex just in cardboard alone. Very difficult for me to make this. It would crumble, it would buckle, as we might see it in real world. It's pretty nice. But what we have here is everyone saying the transporter caused a moment, a deflection. I guess everyone would have thought it would be caused here if they're just visualizing it, and also here. This is where it's got a heck of a lot of load as far as deflection. I could see a crack happening there. But we also have distributed load over here of this area. But they used a couple of point contacts. That, wow, they're amazingly shy, and they're towards the outside of the deck, which puts it more in the post tensioning. It does put it in the post tensioning of this deck. So the post tensioning took the load of the entire structure. Again, this is roughly where it failed, but we have a couple of reasons we could point to there. You know, you could keep driving back to this guy was loaded there in this overhang, but we didn't have failure. We did have a crack somewhere, and a crack could be here, as I'm sort of noting here. The crack could be here, and the least place I would think there would be a crack at is where everyone might think it would be is here. My thinking is, if the crack was there and you were trying to crank this guy up, all you're doing is making the crack fail. You're making it come to, total failure. It's no longer a crack. You're making you're expanding on the crack. So I don't see the crack being here. I don't see it being here. I don't see it being anywhere in this zone here. As you pull post tensioning here, you would be, if the crack was anywhere here, you would be creating an issue. Same thing here. I'd have to make a sort of a circle zone there also that would show the crack's not there. Now, the crack being here is a possibility, and the crack being here is just my guess. And the crack is insignificant unless it turns out to be significant. Crack could be way down here as far as we know. Okay, so you have your loads, the gravity and the weight of the bridge trying to push down on this guy, on this overhang. Again, here's your overhang. Again, here's the overhang. It's just very strong. It's a very strong detail, and I don't see it happening just by that alone. But I do see what I'm going to show you in the next diagram. That supposedly, the next photographs, that they had to have the guy the company that transports this, and that was an engineer who bragged about we helped do the transportation of this bridge. They would have been the one that did the monitoring, making sure that this wasn't just haphazardly placed there. that the transporter wasn't just haphazardly placed anywhere. In fact, it's supposed to be in the engineering plans, and that's in the next image. With that said, if this was very clearly, it states that you're not supposed to, or it's highly recommended, if you will, the way they word it. See, it must be must, not, things like that. Those two words, must, not. You must do, you must not do, those are the words you look for. And everything else is sort of, well, he did say, you should. Should means I have flexibility to do it, whether I choose or not. But with that said, if this post-tensioning rod was added to take off this load while it was transporting, that's the one thing that they state that you should not do, because they just don't want any tensioning done to compensate for transporting. Okay, so this cable, the other thing is everyone thinks this cable became in transportation was tight, and then as they transported it became loose as they then put it on the deck of the on the top surface of the column. At that point, it's a pier. At this top surface is a pier. Okay. So this guy, if you look at the drawings, the other bridge was going to butt right up to you. The post-tensioning rod didn't have any grout on it, as I could see in any images. So therefore, it could flex and move around inside of the ducts that it was placed in. It's typical to be grouted, so it can then be confined and act with a certainty of what you're applying when you're applying the loads. Okay, would that be just the dead weight once it becomes on the bridge? Once you have dead weight out here, if you had a significant amount of dead weight, this area alone would have a lot of tension on a lot of strain and tension on put tension on the post-tensioning cables. Insignificant as it may be, they still do it. It's still some load. It might be insignificant 100% because they might have they obviously compensated. So we're talking about the transporter and the loads. If the transporter was put here, as it appears roughly it was, and it has a couple of contact points, and then it has a large space, and then a couple of contact points again, as per the image that I saw online, images. In other words, it's not fully supported. The underside of this deck is of a tapered design, and they supported it not fully, but in parts. Putting all the load, it appears, based on the design of the deck, onto the post-tensioning members and somewhat onto the transverse members. And the transverse tendons, there are no transverse tendons. As far as I could tell, they're transverse reinforcement rebar. But there are longitudinal tendons that would have been taking this load as they went down the bridge, and hopefully wouldn't bounce too much. Also, this machine, both loaders, or all loaders in slow motion video, appears they were moving 1 2 1 2 1 2, alternating its lifting, which then puts all the load onto one at a time, which would be 2 positions at a time. As this comes up, perhaps on the other end they could move 2 at the same time, leaving it on 4 contact points at any given time. Ideally, you want to lift them up. They all want to lift at the same time. But again, this was engineered, so the engineering firm was supposed to have done the calculations on that, which I find amazing because we only have one post-tensioning area here able to cause the upper deck to fail, and then and then the lower deck failed. You know, they're tied together. These guys work together. The upper deck canopy is part of the lower deck structure as far as taking loads. At one point, including and transferring over to the end columns also, these piers, end columns into the piers. So as I showed you in the triangle, if you will, is that the loads, if you try to push down on this guy here, all you're going to do is transfer the load here, put this one in tension where it's trying to pull this one down, but then it also has to pull, if you know, it can't push down, in other words, but in traveling, it wants to push this one down, but everything's tied back around in a circle. This has post-tendons in it. This guy, I'm not sure. Nevertheless, I don't know if any cracks are observed in it. Once we get this onto the pier, though, now if you try to push this guy down, it's just in compression. Nothing's going to happen. It's going to go down to the earth, if you will. The load path brings it down to the earth. Nothing's going to happen. You try to compress this guy. The load wants to travel down it to some degree, and some of it wants to kick out and fall away. But being that it can't fall away, it wants to push down this side. And with that said, both of these guys want to push outwards. If you're trying to push a load on here, both of these guys want to push that way and this way. The bottom part then keeps it in tension along with the post-tensioning cables. And I'm going to clip this and show you. So now we have this guy. So then if we remove the bottom post-tensioning altogether, and we're just going to do it smoothly. Here we go. Now, when I push against the top, I need to put this on something else, and I'm in luck. Okay, so there's our pier. It's off the grade. As I push against, and get you out a little bit. I'm going to hold it here, and on the other end it's just sitting on that. As I apply a load here, see the way it wants to open up? See at the bottom? And that's just a load there. See if I can pin it this direction and push. As it pushes down, it wants, so that's showing you which way the, and let me put my hand loosely there so no one thinks I'm pulling a trick. So, and we also see rotation, positive and negative. So, that is what's going on here. This has post-tensioning in it though, so at that point it can't pull apart. So you can see how the loads race around this this guy here for a second. So now let's add a post-tension cable. How's that? Imagine it was post-tension. All I did was put a cable in there. You can now visualize that as this guy tries to pull apart, again, same load being applied, that the cables now will take the applied loads. So they then become under more tension as they try to, as the deck tries to pull them apart. We also have the concrete though, and the reinforcement. All this helping. Although they're, I think, only thing that's going to keep this together in this direction pretty much is going to be the post-tension cables, because this is lying flat. It's already got its own dead weight going against you, trying to create an issue with opening up itself under its own dead weight load, ultimately transferring the load back to the canopy and to the end columns. So you can imagine now that even a crack here, the post-tension cables are still going to be in play. This is going to create a lot of stress on this area though, around this area. That's fully through obviously, but we're not there. And this is glued on, so I don't know how it's going to react. It's going to play along with this, but let's see if I hold it and add the load again at the top. Yeah, I'm adding the load at the top again, and you can see that it's not. You can see slight flex down there. That's because I can only pull this so tight and hold it with my fingers, but you can see now that it's not opening up. So this is what post-tensioning is about, and how you can maybe visualize it better in theory. Accelerating this whole video, I hope, shows you that each one will have now post-tensioning on it. So this one, you're not allowed to, per Florida Department of Transportation specs. They looks like they pretty much are following the federal highway specs. That during transportation, you're not allowed to add post-tensioning just for transportation reasons. The deck basically has to be designed, the structure has to be designed to support itself during transportation, wherever these are located, wherever this is designed, or however they design it into the whole transportation final drawing. Back to the node then. So now let's just add a few more post-tension cables. And let's show why a post-tension or statewide post-tension cable in this column that was never spec'd could be a positive thing. If we know one was down here roughly, we know that by the NTSB's video, and we assume another one's up here based on what we saw anchoring, hanging at the base on the wall, etc. But as these loads are applied, as I was telling you about, it wants to push this apart. At some point, the load stress might be so great, though, it tries to put a bending moment in this. To counter that bending moment, you then have post-tensioning to add more strength on the bottom of this, where it's going to be under tension, down here pulling this way and that way. But remember, it's confined also. It doesn't have the ability to go anywhere, so it can flex and buckle. But these loads have been calculated in this column sizing. Well, it was calculated to take the loads. The redundancy would be if the post-tensioning, if everything was, the post-tensioning was just redundant. That would be nice. That would be nice. All right, so then across the top here we have the other post-tension cables. Only 2 on each side at this time of their post-tensioning, as I could tell per the images. And combined is supposed to have 6 as far as the drawings show. And also, I think those 6 come into play when the other part of the deck comes through. It literally goes through this deck into the next deck. They post tension from the opposite ends, as far as I can tell. So same thing with this one. You could have another post tension cable down here to compensate. I don't know if they did or not, but remember the loads, how they're going to, when you press here, how it wants to bow this out. It's just like standing with your legs apart and add the loads. They just want to open up. So the load's going to pretty much go here. With that said, they also want to collapse down, which makes it weak and at this section here. What stops it from collapsing downward is the post-tension cable across the top. It's locked in at the end. It's in a position. So you have this guy here, this pen now. It's rigid. As you apply this post-tensioning load, keep cranking down on it, you start, this pen now becomes this string. You start bending this string, the strong back, the post-tensioning cable that holds together. As you start doing that, you put this guy under such stress that the load was designed to go across. You now invert it at that point, just inverting it. So I'm going to exaggerate a little bit here, and exaggerating. So this is the post-tension cable going across. This guy right here. And that's where the node would be at that section, pushing down. At some point, it pushes, it deflects the post-tension cables. This is what I theorize. Now, it may only deflect it a little bit, but remember, it's carrying half the bridge load down here. The supports aren't there anymore. The entire bridge is installed at this point. So it was the load transferring down here and down this column. When you flex this cable by changing the moment, the point where the bridge is supposed to be transferring the load down the column, when you compress this node, you then change the path, the load path. It goes down this column at this point. It goes down this column, and that's where you see it goes down this column. But at some point, I see 2 breaks back here. I see 2 breaks back here. So as you're compressing this guy, these 2 must have held up as long as they could, and that must have had more strain than the rest of the cable, because I think it broke here and here at the same time simultaneously. The deck started failing. The load was the dead load of this upper deck, all the truss, and the lower deck were too much for the entire structure to maintain its integrity. All the dead load, once this cracked, once it broke, once it pulled so much tension down here, I'm assuming it's this one. Once he pulled so much, and not this one incidentally, that's what I'm assuming. So once you started pulling that tension down there, and I could reverse it, it can work either way for me. I don't care if there was a way to tension this one. It still comes to the same conclusion that you changed the point. You changed the point of these top two, only two on each side, span so far apart that I could easily see that these guys, let me show you a bit. So I could easily see that if the two posts, and my position might be off on this, but remember that's the deck, what it looks like transversely. And if we only got two post tensioning cables there, and we have the node, easily visualize that if this load was being applied, and I showed you how the truss works, the load is forcing these two outwards. They're doing the same as I showed you before. Let me make sure I've got a little bit of a video image in there. As this applies to the top, as you apply load to the top, these two want to push out, right? As I push down, if they're here, as I pull down, and these points are here, they want to push out. And when they push out, you can lower. See how it can lower? So, you also need to find a crack. As these push out, you'd ideally like to find a crack going across, all the way transversely across. As this pushed down, this would have created expansion in the materials, obviously, and the material is not going to expand. It's not going to grow itself. It's going to crack. That would, as it comes apart, what we do have a crack, as you can see in the image, as in the failure. We do see a crack, obviously, an obvious crack here and here on our failures. Also, as I said in the video, in the earlier part of this video a few moments ago, that I saw that in the slow motion video that it appears to be two other failure points. So basically this cable flexed. Once it flexed, the load of the entire structure, the point load changed to this point. It tried to transfer the load down. It didn't try. It transferred the load down the column at that point. Down this column and down that column. And that's where you see the lower deck fail. This didn't fail. It was too structurally strong. You know, it was too supportive of everything. It had too much going on that was not the first point of failure on this lower deck. It was over here, where it's out in the span and where the loads were. So it was transferring down both columns. But this, being out here unsupported from a pier, it has nothing out there. This is where all the load. It found the weakest. This is the weakest point of these two pushing down, as I showed you. When they push down, they want to push out. So it broke that point. Broke this point. Pushed this down. Broke this. Pushed down the upper canopy. Flexing this. These two cables, I think, broke here. Both of them. Not the cables. Let me correct that. What broke here, I think, might have been first initially the decking, and then the cables gave in. But here is where the point load changed. It no longer transferred to the end of the deck down the columns, down the column number 12. It changed it to there. This deck was not designed to have the entire structure load transferred to number 10 and number 11. It was not. The entire structure was not. I said deck. This entire structure was not designed to transfer the load to number 10 and number 11. And when that transferred, because of the post-tensioning of these cables, there's your simple collapse. All right, I think that's hopefully it's one of my last videos. Okay, here's some online information that was found under Florida International University's website. You can pause and read the information, but some of it's kind of ironic where they refer to the bridge being number one, and if it fails, basically that would be useless. Um, hmm. And there's the structure, the harmonic conditionings of natural frequencies, the stays, and the pylon. So they are structural in that respect. Here's the initial or the plans, initial location of the transporter and temporary lifting. This is how they're addressing how the inspection should have went with gamma and density logging. That's how it should have gone. I don't know if it did not or not. It would have been pretty fast if they did do it in that short amount of 2 hour period that they spoke of the cracking. Here's the monitoring. Um, it's amazing. You got to pause it and read these things. Um, but it's what I found of interest. People referring to a lot of things online, a lot of these groups, and referring to different things. Here's the real, appears to be the contractual data. All right, wish you guys all the best. Thanks for subscribing.